So hello, welcome to the second part of my videos on equilibrium, or the equilibrium of rigid bodies, as written here. I'm going to follow a similar format to the previous video, in which I just cover a few, shall we say, theoretical points, or a couple of theoretical points, and then from there go on and look at an exam question to see how it works in practice. So I've written excuse me, I've written two extra notes in addition to the ones I discussed in the previous video. First one is resolving. Now this is a technique that you should have learned already, so I won't be describing it in detail, but it's the basic idea that if we have equilibrium, it means there is no resultant force in any one direction. So if we are considering the problem in a plane in 2 dimensions, it means that we can choose any particular direction in that plane, and we can use the fact that the resultant force in that direction is 0. We can resolve all the forces, find their components in that direction, add them up, and they must sum to 0, considering signs. And then, having done that, we can look at the direction perpendicular to the first direction we looked at, and the resultant force in that direction must also be 0. So basically I'm saying that if I were to draw some random blob and say, okay, this is an object in a plane, and I can simply choose one particular line inside that plane, add up the components of all of the forces along the direction of that line, that one from there, that one from there, that one from there, and I know that the sum must be 0, and then I can choose the line which is perpendicular to the first line, and I know that the same must be true. So this technique we, namely you, should have already used if you studied M1 or a similar A-level module, like perhaps Edexcel, I don't know, M1, M2, M3, I'm not sure which, probably M1. Anyway, so resolving forces is a fairly basic topic which I won't cover in detail here, but we will use it, of course. A significantly more advanced idea is using this word toppling here. Now, before we go into toppling, let's first quote Lami's theorem, and I won't prove Lami's theorem in the way that I tried to prove in the previous video. What was it? What did I prove? I've actually forgotten. I proved something about something about the fact that we can choose any pivot. Yeah, we can choose any pivot. If we have rotational equilibrium, the sum of the moments about any pivot is 0. Now Lami's theorem is something slightly different but closely connected, which is basically saying that it's a specific theorem for 3 forces. So if you have a body on which acts exactly 3 forces, I'll come back to that point in a minute. And if you know that this object, let's just choose 3 random whoops, that's supposed to be a line, F1, F2, F3, let's say. If you know that the body is in both linear and rotational equilibrium, so that it is not moving and it is not rotating, Lami's theorem says you know 2 different things, both of which are very useful. The first thing you know is that the 3 forces form, you guessed it, a triangle, yeah? So this is something you almost certainly have learned before. The 3 vectors representing the 3 forces can be formed into a triangle if we consider the lengths of the vectors, of course, should be the magnitudes of the vectors. So that's the vector triangle idea, which is familiar to anyone who's studied vectors, which is the resultant of 2 forces is the third side of a triangle, isn't it? Yeah. So you've got B, C, A. B that way plus C going up that way would give A going that way. That's the basic idea of vectors. Of course, it's very slightly different to that here, because what we're saying is that the sum of the three forces is 0, but that's almost the same thing, because we're saying F1 plus F2 equals F... Sorry, actually it's not that way here, is it? It's... yeah, we're saying F1 plus F2 plus F3 equals 0, if treated as vectors, of course, not as numbers. Excuse me. Which is almost the same thing, because it's like saying minus F1 equals F2 plus F3, isn't it? So that part of Lami's theorem is basic. It's let's say, is knowledge you almost certainly already have, that if three forces are in equilibrium, they form a vector triangle, a complete triangle. But the other part of Lami's theorem you might not, or you almost certainly wouldn't know at first, is that the lines of action, so it's probably best to write this in English, lines of action of three forces coincide at one point, or meet at one point. And this is a very useful fact. Now, looking at my diagram here, I can see that it's clearly not true, is it? So this object would not be in equilibrium. It would, at the very least, it would rotate. And we see that because if I draw the lines of action of the force, so think of it like this. A force has a certain length and it has a direction because it's a vector. But it also has a position at which it acts. Now, it's not really the case that it's one position. It's more that it is one line of action. Yeah. So think of it as a force has a magnitude, a direction, but also a line of action. And I'm drawing those lines there. Now we can see clearly here that this object cannot be in equilibrium. And why is that? Because if I choose this pivot here, remember we say that we can choose any pivot. If I choose the pivot point P, I can see that the lines of action of F2 and F3 pass through P, well, more or less on that diagram, that's good enough, which means that the resultant moment about P would be entirely from the force F1. So you'd have some distance d here, which is the perpendicular distance of the line of action of F1 from the pivot P, and you could write down that F1 times d is the net or resultant moment on the body. So the body will definitely rotate because it's a non-zero moment, isn't it? So we can see here the sort of negative of Lami's theorem. Lami's theorem is telling us here that the object cannot be in equilibrium, but more usually we will be presented with an object which we are told is in equilibrium, and then it may be, I emphasize it may be the case, not necessarily, that Lami's theorem will allow us to do some calculations more quickly. I hope to show you an example of that in a minute, but here I'd like to maybe redraw this diagram so that Lami's theorem does apply. So let me draw another random object. Yep, okay, another random object. And another three forces, so I'll draw F1 acting here. And I'll draw F2. Where shall I draw F2? Doesn't really matter. F2 acting like that. And now I'll draw the lines of action of these two forces. Obviously it extends in both directions, but that's a bit pointless. And we can see that the lines of action of these two forces, as indeed any other two forces which are not parallel, that's a very important detail, will obviously cross at a single point. So if you want this object to be in equilibrium under the action of three forces, then the third force must have the property that its line of action passes through this point here. So all I need to do now is consider, well, if I want equilibrium here, I know that I've got a triangle something like this. F1's going that way, F2's going that way, so F3 will need to be in some kind of direction like that. But it will also have to have its line of action passing through that point, which means I probably want something like, I mean obviously this is not being measured, it's just that for illustration, something like that. Obviously the magnitudes are also important, but this is a situation which could theoretically be equilibrium if the measurements were correct. All three of those forces pass through one point, and their directions and magnitudes are such that they might form a complete triangle. So that's the basic idea. Let's not forget one extra detail though that can be important in practice. Suppose there's a fourth force. Now Lami's theorem is talking about three forces, so in theory we can't apply Lami's theorem. But don't forget that any two forces can be combined into one force, the resultant. So for example, you could convert F1 and F2 into F5 or something. Oops, what am I doing? You can't erase like that. F5. F1 plus F2 could be changed to F5, and then we could combine F5, F4 and F3 and then apply Lami's theorem. So to quickly summarize two elements of Lami's theorem: the three forces form a vector triangle and their lines of action pass through a single point. And it's that second point, that the lines of action pass through one point, that is useful and might be a new technique to you. So I'm going to show it to you now in the next section. Okay, so how do we use this knowledge, Lami's theorem? Let's consider a case that you would have considered. Sorry, terrible English sentence construction going on here. Let's consider a situation that I'm sure you've looked at in earlier mechanics studies, which is a box sitting on a slope or ramp. So let me try and draw that now. I've got some kind of ramp and I've got a box. Okay. Now, as we all know, let's say this very carefully. There are two things that could happen in this situation, which I'm sure you've studied before, but there is a third thing that could happen that you may not have studied. So let me pose the question like that. Three possible behaviors in this situation. Perhaps I should just write three possibilities, it's less confusing. What can happen if you really do set up a box on a ramp, place the box on the ramp? There are three things that can happen, correct? If you can't think of three, think carefully, there is a third one. Okay, so the three things are: first, nothing can happen. In other words, we can have proper, real equilibrium. Also, perhaps the most common possibility would be sliding. So the box would simply, let's write this box and ramp. The box would simply slide downwards. It's not going to slide upwards, I think, if we just place it on the ramp. But what's the third possibility? The third possibility, I hope you realise, is what we would probably call in English toppling. So toppling is the case of this movement here. So rotation, in other words, of the box. And also I want you to notice, if we talk about rotation, we usually, or not usually, we must talk about rotation around one point, yeah? Think of rotation in more general terms. Obvious example, a wheel, the wheel of a car, the wheel of anything, rotates around a centre, doesn't it? So the centre point doesn't move. Now, not all rotation is exactly the same, is it? Because we could also have rotation of a wheel about, let's say, the point X. That would mean that we'd get this case. We'd get this, and then, this, and then, this. So in other words, X being fixed and the circle, whatever it is, I'm just imagining a random object rotating about that point. So that's actually a slightly different physical process, isn't it? You can see that. But in any case, any kind of rotation will mean rotation about one fixed point. So why do I bring that up? Because if we do have the box toppling, which could be said as just in more normal language as just falling over, the box falls over. If the box topples, then it rotates, and about what point does it rotate? In other words, what is the center of that rotation? So after a little thought, I hope you can see that it's this point here, precisely this point, isn't it? Now there is some slight complexity there. I must be clear that it is possible to have both sliding and toppling happening at the same time. That is the most general form of motion, which is where an object is both rotating and moving along a line. That's actually much more complicated, and that kind of motion will not be covered in your exams here in this syllabus. So we're now going to focus on the case of toppling only. So toppling only would mean, in fact, rotating about this point here. So our pivot, let's be clear, will be the sort of the leading bottom corner. Well, you can see. Now, what was it I wanted to tell you about this? I've actually forgotten. Yeah, so we're analysing toppling, and we're considering how do we analyse it in terms of forces. So the first thing I want to note is that when we're only considering sliding, we can afford a simplified model. If we consider only sliding so that we're not interested in rotation, then we would usually draw the force diagram for the box, or let's say, again, the free body diagram of the box. Let's actually remove the ramp and draw a free body diagram of the box. So when we're studying M1 in CIE, or the equivalent in EPICSL, we don't bother to worry about the positions of the forces. We just draw the forces' directions, don't we? The friction acts up the slope because it's opposing motion, and the weight, well, some people will draw it in that position, which is correct, some people won't, but it doesn't matter because we're not worried about rotation. So in this case, all we have to do is resolve. Remember what I said at the beginning? Two things I'm thinking about today: resolving and Lami's theorem for toppling. So if we're not considering toppling, we just use resolving, and we get these formulas like, this is theta, and then it's like F equals W sine theta, and N equals W cos theta, and so on. And I won't go over that again because that's basic knowledge. But if we are considering toppling, well, there's one significant change that comes in, which is, and let's draw the box again, the significant change that comes in is that we must consider the positions of the forces. Yeah. So now I'll try to draw the box again, a little bit larger maybe. So again, imagine the ramp. I'm drawing a free body diagram of the box. So I'm only drawing the box and the forces acting on the box. Okay, so let's consider each force in turn. First, the friction. The friction must act along, or let's say at, the surface of contact. The surface of contact is down here where the box meets the ramp. So the line of action of the friction is obviously along that surface. I'll use blue dotted lines to indicate lines of action of forces. So that's friction. What about weight? Well, weight is easy. Weight always acts through the center of mass. So if we happen to know that the box is a uniform box, what does uniform mean? It specifically means uniform density. So the density is the same at every point inside the box. So if that's the case, then we know that the center of mass of the box is in the geometric center, and the geometric center of such an object can always be found using lines of symmetry. I should probably make a separate video about centers of mass, actually. It's an important extra topic, but I expect nobody will find any difficulty in understanding this concept. Well, that doesn't help. Oops, that's going to take a long time, isn't it? I'm trying to get rid of a dotted line stroke by stroke. Okay, so the weight obviously acts vertically downwards, so we know its line of action because we know the position of the center of mass in a uniform box, and we know the direction of gravity. So that much is easy, right? Now ask yourself this question, bearing in mind what I already said about Lami's theorem. How and where should we draw the normal contact force? Excuse me for the drinking sounds there. How and where should we draw the normal contact force? Okay, so if you were paying attention, I'm sure it's obvious to you that the answer is we consider the point. We consider this point here where the two forces weight and friction coincide or meet. Those two lines meet at that point, so the line of action of the normal contact force must go through that point. If we do indeed have what am I saying? If we do indeed have equilibrium, both rotational and linear, we must have Lami's theorem holding, because there are only three forces, remember, so Lami's theorem does apply. We also know that the normal contact force's direction is always perpendicular to the surface of contact. That was my big thing to teach you in the previous video. So therefore we finish the problem. We know that the normal contact force acts like this. And again, it doesn't matter exactly where you draw the force. What matters is that you have the correct line of action. So this is the force N being normal contact force, and that is a complete free body diagram of the box. In equilibrium, I should emphasize, if it's in equilibrium. Okay, now you might have been a little curious or confused about that idea of where the normal contact force acts. You may have previously thought that the normal contact force acts through the center, something like this. But actually, thinking about it, you should see there's no real reason for that to be true. And then you start to think, well, how does the normal contact force really work? Well, what's really going on is that there's actual interatomic forces happening at each point, right? After all, what is a normal contact force in terms of physics? We've got the ground and we've got something standing on the ground. The forces between them are electromagnetic. What do I mean by that? Well, of course, if the ground is not ground, but if it's perhaps water or gas, then the object will fall through. What's the difference between solid and liquid and gas? The answer is that in a solid, the atoms hold their position relative to one another through interatomic forces. The forces between atoms are electromagnetic. They're to do with electrons mainly. So we've got at the atomic level, we've got these forces happening between the atoms of the box and the atoms of the ramp, haven't we? So we've actually got lots of little forces pushing upwards, repelling forces, all along there. However, there is no special... Now, if all of those forces were equal, then of course it would be the case. Let me draw another example. Oops. If all of the forces along the bottom of the box were equal in magnitude, then adding them up effectively one would get, well, in terms of their turning effect, in terms of their moment effect, then the average effect would be the same as if all of them were in the middle. I'm not sure if I've made that completely obvious and clear to you, but like we were saying in the first video, well, it's not exactly the same, but it's to do with the linearity of the formula for moments, the fact that moments are force times distance. It's almost like saying the effect of all those forces is like the sum of them times the mean or average position. I don't think that's a very good way to write the formula actually, but never mind. I mean, it's not like it's a real formula, so don't worry about that. So what I'm trying to say, and you can investigate this further if you want to properly understand it, but you don't need to, is that there are lots of those little forces, and what effectively we're doing by drawing a single normal contact force, it's a simplification, but it's a simplification which works because in effect we're taking the average position of all those forces. excuse me, the average position of all those little normal contact forces, so we're kind of bundling them up into one force. Okay, so as we said, if it were the case that all those little forces were equal in magnitude, then it would be the case that we would have to draw the normal contact force through the middle. But we don't do that. What we actually do is we draw it here because we have equilibrium. And so how do we get equilibrium? Well, the answer is that all those little forces are not equal. The ones nearer the bottom are bigger than the ones nearer the top. Okay, so the average position of them, thinking of it as a weighted average, is closer to the bottom than the top, and that's how the system manages to achieve equilibrium without toppling. Now think about something which I used the word for, but I didn't show you yet, the idea of what would that diagram look like if the box did topple, or let's say just before it toppled. Let's take an extreme case, a very tall, very thin box. Okay, this is not very good, is it? I'll try and draw straighter lines here. Oh, I suppose that's good enough, maybe. Maybe. So clearly this box is going to topple, right? Assuming it has a uniform distribution of weight. So why is that? Well, it's because if we were to draw the line of action of the weight, it would look like that. And we already know the line of action of friction is like that. So the point where those two lines of actions meet is here, P, and clearly the average position of the contact force cannot be, you see what I'm saying, the average position of the point where the line of action of the normal contact force meets the box, that point there cannot be outside the box, because the normal contact force can only act through those points of contact, obviously, between the box and the floor, the ramp. So what happens in this case is that the normal contact force acts entirely at the front corner of the box. In other words, we go from a situation in which we originally just had a sort of a larger force here than here. We eventually reach a point as boxes get closer and closer to toppling, when effectively there's just nothing here at all and one big force at the corner. Now, another way to understand that, probably easier, is to consider the situation where something is just about to topple. So let's draw a case where an object is, again, a box on a ramp, is just about to topple, and then I think it's a little more obvious what's going on. So I'll draw the ramp just for clarity. Now I need to somehow get this right. Let me draw the weight force first. So there's the weight force, and I'm going to consider the case where the normal contact force, where we're just about to topple, which means that at that moment we still do have equilibrium, but the equilibrium is about to be broken. So what I mean is that the box itself, its corner, lies at exactly that same point. Whoops. Well, okay, that still works, I guess. Something like that. Yeah. Okay. Okay, not a perfect diagram, but it's good enough. So now N is acting exactly at the point of intersection of the lines of action of the three forces: friction, contact, and weight. And it should perfectly make sense to you now why that the contact force is fully acting at that one point. Because suppose the box is about to topple, and then suppose it does actually topple. So in other words, suppose this floor of the box just moves up slightly. Whoops, that's not slightly, is it? If the floor of the box moves up slightly, then what's happening in that situation? You know, something like this. Sorry, that's not very good. But in that situation, you can see that now the only contact between the ramp and the box is at that point. So it makes sense that the entirety, the whole of the normal contact force, acts through that point when the box is just about to topple. So what I'm trying to teach you here is the idea of just about to topple, which should be very familiar in analogy to the idea of just about to move or slip. So if you remember, and I hope you do remember from earlier studies, just about to move or slip implies that the friction force is equal to the coefficient of friction times the normal contact force. So just about to topple, we now discover, implies n acts at corner. I can't explain it more clearly than that. It acts at the corner, which is the pivot of the rotation. Yeah, that is the point which does not move in the rotation of the object. Okay, so that's a sort of explanation of toppling as best I can manage. I think that's the kind of level at which you need to understand it to do the exam question. So what I'll do now is show you an exam question, and much like in the previous video, I'm going to do it in real time, because I've actually, although I answered all these questions before, I don't really remember them all. So excuse me if my methods are a little less beautiful than they might be. But maybe that's also helpful to see the teacher kind of struggling with it a little bit, although I don't think I'll struggle very much. But anyway, let's look at the question we're going to look at today. It's here, yeah. So I don't know if you can read this clearly. As is very often in these mechanics questions, we have quite a lot of text to get through. But equally, the good news is that they give us a diagram, so that really helps in understanding. So let's have a quick read through together. If you like, you can pause the video and try and do the problem on your own. Absolutely excellent idea if you do that, but not necessary. No, that's a bit too big, isn't it? Maybe 175%? Yeah. So we have a uniform solid cube. So uniform already helps us. We know where the weight acts. Edge 1 meter, so the length of the edge of the cube is 1 meter, the weight is 200 newtons, and it's on a rough, notice the word rough, horizontal plane. A light rod AB of length 1.2 meters is smoothly hinged. Now we mentioned hinged in the previous video, but I'll come back to that if I need to in this example. At point A to a point of the plane, and hinged at A, obviously, so A is the end of the rod. A is hinged to a point of the plane. B is in contact with a smooth face, important word smooth, no friction, of the cube. It doesn't specify where B is on the cube, probably doesn't matter, so we'll come back to that. The rod lies in a vertical plane perpendicular to this face and passing through the center of mass of the cube. So that sentence, as is so often the case, is really just telling you that you can treat the whole problem in 2 dimensions. The plane containing all the points A, B, F, E, C, D and the center of mass of the cube is just one plane. So we're doing a 2-dimensional problem, not 3-dimensional. The rod makes an angle of 30 degrees with the horizontal. A gradually increasing force of magnitude P is applied vertically downwards at the midpoint of AB until the cube is on the point of turning. On the point of turning is exactly the same meaning as just about to topple. I forgot that you can say it that other way, yeah. So turning and toppling are basically the same in this case. On the point of turning about the edge through D. Okay. By considering the forces acting on the cube at this instant, so that's slightly unusual. They're actually telling you exactly what to analyze. I may come back to that. Find the normal contact force at B and hence show that P is equal to something. And I think that's the end of the question. Oh no, there's a second part. Let's do the first part first. Okay. So I think I've drawn the diagram on here somewhere. Here it is. Oops. Maybe that's a little bit too small, is it? Yeah. Let's make it bigger because we want to draw on it as well. So there's the diagram. And excuse me, I'll have to flip back and forward between the question and the diagram sometimes. So The first thing I'm noticing is they're telling me to consider the forces acting on the cube. So if I'm drawing a separate diagram, which I'm not right now, but you probably should, you should probably just draw the cube free body diagram without the rod. And on that diagram you should annotate all the forces acting on the cube. So here's the question again. If you want to, you can pause the video, and if you like to sort of do this in real time, you can try and do that now. Draw a free body diagram of the cube with all forces. Okay, I'm going to continue now. I've forgotten what I'm doing. By considering the forces acting on the cube, find the normal contact force at B. Now I know that the cube is on the point of toppling, or on the point of turning. Whoops, I'm in the wrong thing here, aren't I? So, if I draw the forces directly on the diagram, what have I got? I've got the weight already there. I know that because it's on the point of turning about D, imagine it moving that way, that means that, as we've just discussed, the normal contact force on the floor is entirely at D. So I need to draw the other forces acting on the cube. I know there's a normal contact force between B at B, so I'll draw that. Now here, of course, there's no, let's call this NB, let's call this ND. Here, of course, there's no confusion about the position of the normal contact force because it's a single point of contact here. It's not a surface contact. Okay, so have we got all the forces acting on the cube? No, I think there's friction as well, isn't there? The cube rests on a rough horizontal plane, which means there will be friction between the cube and the floor. But B is in contact with the smooth face, so there's no friction there. So let's also draw the friction force acting along the surface of the plane, which would be this way. Now, is it obvious that the friction acts to the left and not to the right? I think it is obvious, isn't it? Because after all, if the friction were not there, what would be the linear motion of the cube? Of course, it would go to the right, not to the left. So the friction must act to the left. And I think I'll just call that F, not FC, because I don't think there are any other friction forces. Right. Okay. Now, what are we trying to? I often have this problem. What are we actually trying to do? Find the normal contact force at B. That's the task. Okay, so we want to find the value of NB. So, I think you would agree with me that if we consider the possibilities, we have resolving and we have finding moments about particular points. Now, what about Lami's theorem? Lami's theorem. Can we apply Lami's theorem here? Well, no, we can't apply Lami's theorem immediately because there are 1, 2, 3 forces acting on the cube. It doesn't mean, as I said before, that you can't apply Lami's theorem by first combining two forces, but there can be also some difficulties with applying Lami's theorem. I can't remember the details, but I think that if forces are parallel, it causes a rather serious accident for Lami's theorem. And since I can see here that we have two pairs of parallel forces, Lami's theorem is definitely not what we want to use, at least for this part of the question. All right. We've got moments and we've got resolving. Now, resolving is particularly simple here if we do it horizontally and vertically. So let's do that. Resolving vertically first, I get ND equals 200 newtons. And horizontally, I get NB equals F. So that doesn't solve the problem immediately because we want to find NB, but we don't know F yet. And I don't think we know the coefficient of friction, so that's no good either. Well, anyway, forget that. However, if we resolve if we take moments about one particular pivot, I think we should get the answer the answer immediately. If you saw that, then well done. So if we take moments about the pivot D, we can clearly see that the force ND has no net moment and the force F has no net moment, so only the forces NB. Hold on, do I know? Oh yes I do, yeah, that's important. The forces NB and the weight have any effect. So the counterclockwise or anticlockwise moment is caused by the weight, and it's 200 times half the side of the cube. The lengths here are 1, so this is 0.5, 0.5. And the clockwise moment is NB times the distance, and let's just kind of draw a, I don't know what this is, point G or something. NB times DG, and DG equals BC, and BC equals AB sine 30, which is 1/2, sine 30 is 1/2 of the distance AB, and I think the distance AB was 1.2, which is 1.2 is 6/5, so I have 3/5 or 0.6. So I can therefore deduce that NB is 1/2 of 200, or 100 over DG, which was 3/5, so it's 500 divided by 3 measured in newtons, and you can convert that to 3 significant figures if you like. So that part was fairly straightforward, but of course only a student who understands properly the significance of the phrase on the point of turning in that long paragraph would be able to get it. Right, now hence show that P equals something. So how's that going to work? How are we going to find the magnitude of P given that knowledge that we just discovered? See, it says hence, yeah, so we must use what we've just learned. Well, I would say we almost certainly need to draw a free body diagram of AB. If we want to find P, clearly we're going to have to do it by considering the forces on the rod AB. So let's try and do that. So there's the rod AB. Now remember, we're hinged at A, and at the point B we have the force NB, but using Newton's third law we recognize that the magnitude and direction of the force acting on the rod at B are equal and opposite to the force acting on the cube at B, so it goes to the left and it has magnitude, well, we'll just call it NB, but we now know that's 500/3. The rod is uniform, I believe. The rod is uniform. A light rod AB, oh, it's light, I'm sorry, it's not uniform, it's light. So if the rod is light, then it has no weight, so we can ignore weight. So we should consider what other forces we have. We have P acting through the midpoint, so I'll draw that here. And then we have to consider the excuse me. Interesting. Then we have to consider the contact force at A. Now, what did we say about hinges? We said that if there's a hinge, you don't actually know the direction of the contact force in advance. You have to work it out. And usually the best way to deal with that is to break it down into 2 components. So let's call this N1 and N2. So we see we have quite a simple system here where yeah, we have quite a simple system here. Sorry, I forgot what I was doing for a minute. What I'm actually trying to do is find P. So in order to find P, well, I can say we don't know these, but actually it's more accurate to say that this one is just equal to this one and this one is equal to this one. So n2 is nb, obviously, and n1 is equal to p. Maybe I'll just write that. But that doesn't help us to find p, of course. So in order to find p, we should take moments, right? Hope that's fairly obvious by the same logic as before. NB is obviously going to be 1/2 of p, isn't it? Sorry, am I being an idiot? Yes, I am. You have to consider trigonometry here, geometry. That was very stupid. So this angle is 30 degrees. So we simply need to consider the p, the clockwise moment is p multiplied by, let's say, what is it, 0.6 times, right, perpendicular distance is cosine 30 is equal to NB times 1.2 times, what is that, sine 30. We have 30 here, so at this perpendicular distance, sine 30. So just applying the principle of moments, I get P equals 2NB over root 3, isn't it? Oh, tan 30. Yeah. Which is 1000 over 3 root 3 or something like that. Yeah, I think that's the same as the answer, isn't it? 1000 root 3 over 9. Yeah, same thing. Okay, so nothing too demanding so far. This is not a very difficult question, to be honest. Only difficult thing is that you must understand the idea of toppling, or on the point of toppling. Then it's fairly easy, as you can see. But anyway, we're not finished. There is another step. Find the set of values. Well, that's a confusing question. Find the set of values of the coefficient of friction between the cube and the plane for equilibrium to be broken in this way. Right, so here you have to read back to the beginning of the question. What was it saying? It was saying that... Yes, you see, this is... I think this is an unfortunately confusing way of structuring the language. It says, a gradually increasing force of P is applied at the midpoint of AB until the cube is on the point of turning about an edge through D. So what they mean is we keep increasing P until at some point the cube starts to topple, starts to turn around D. And what they're saying is that it does not, on the other hand, break equilibrium in the other way, which would be for it to slide. So in order to... what we need to find is an upper and lower value. It says set of values, an upper and lower bound on the coefficient of friction for that kind of toppling to occur. So my first thought is that I consider this situation that we already analysed, and I say, well, if that setup obtains, if this happens in exactly the way that I've calculated, what do I know? I know the value of ND, 200, and I know the value of F, meanwhile, would be equal to NB. Because if the value of NB were bigger than F, then we would get sliding to the right. So if we don't get sliding, it's because F is equal to NB. So let me write that in English. So if, this is like part 2, if no sliding, then F equals NB, which was already figured out to be 500 over 3. And, well, whether they're sliding or not, it's true that ND is 200. Therefore, F over N is whatever that is, 5 over 6, is it? And we know that f is always less than or equal to mu n. Therefore mu is bigger than or equal to f over n, which is 5 over 6. So there I've found the lower limit on the value of mu, the coefficient of friction. I believe I've got that right. Now, but it says a set of values, so if I've found a lower limit, I think I need to find an upper limit as well. Now, what would that be? That would probably be I might need to think about this. What would be the restriction, the other restriction on f? Okay, so it's a good thing I didn't spend too long thinking about that, because actually the question is a bit misleading. When it says the set of values, of course that technically can mean an unbounded set, so it actually means, in other words, there is no other physical restriction. Friction, the coefficient of friction must be bigger than 5 over 6, otherwise certainly the box would slide before it toppled. Yeah, it would move to the right before it toppled, but there's no other restriction. If the coefficient of friction, is very, very large, it doesn't alter this behavior. We still get toppling. Friction force will just simply equal NB, whatever value NB takes. So that question is over. Maybe just do we have? Always think carefully about inequality here. If friction is equal to mu n. Well, anyway, I think that what I've written there is logical, so I think that's fine. So, not a hugely difficult question, but certainly, as far as I remember, students do have difficulties with understanding it. You can see the mathematics is simple, but maybe the ideas might be a bit unfamiliar to you. Oh, by the way, I forgot to mention which paper this is. It's Winter 2007. Question 3 or 2? Question 3. Winter 2007, question 3, if you want to look it up and check it over yourself. So I hope you found that useful. I think I'll do one more video on this topic. Excuse me, on this topic. I'll briefly mention something about centers of mass or centers of gravity. And I'll try to look at one of the harder exam problems, because some of the problems on equilibrium are genuinely quite difficult. So see you next time.